We spend our lives worrying about money, resources, and scarcity. But cosmology proves that in an infinite, eternal inflation universe, every possible arrangement of matter recurs an infinite number of times. There are infinite Hubble volumes where you possess unlimited wealth and own entire star systems. To understand why scarcity is an illusion in an infinite cosmos, we need three things: eternal inflation, ergodic recurrence, and the level 1 multiverse. Now, let us step in. Take a coin out of your pocket and set it on the table in front of you. If you don't have a coin nearby, picture one, a single, ordinary coin resting on wood. That coin is going to carry us a very long way tonight, so keep it where you can see it. Here is what that coin means to you, whether you have ever said it out loud or not. It means there is a fixed amount. A wallet holds what it holds. A shelf holds so much food and no more. A paycheck arrives, gets divided, and runs out. Your whole life runs on a quiet piece of arithmetic. What I have is what there is. One person's gain feels like another person's loss, because somewhere deep down we all learned the same lesson. Resources are finite, and the pie only cuts so many ways. And that lesson is not foolish. It is one of the oldest and most sensible lessons our kind ever learned. It is not even only about money. Look at how you treat your hours. A calendar has room for so much and no more. Every yes you give is a no to something else. Time, like the coin, is a thing you spend. Scarcity is the grammar of an ordinary life, spoken so fluently we forget it is a language at all. The people who worried, who watched their stores, who saved for the lean season, those were the people who made it through. Two researchers, Sendhil Mullainathan and Eldar Shafir, wrote an entire book about what scarcity does to the human mind. And what they found is that scarcity doesn't just limit what you own, it narrows what you can think about. When resources feel short, the mind tightens around them. Scarcity is not just a condition we live in, it is a lens we see through. Why would our minds work that way, narrowing under scarcity instead of rising above it? Because for almost all of human history, the narrowing paid. The authors of a book called Superabundance put the evolutionary logic in one line. The humans that worried, were vigilant, and hoarded food and money survived. The humans that assumed abundance often did not. Your scarcity instinct is not a personal flaw. It is an inheritance, a survival tool polished over thousands of generations of lean seasons, handed to you the way you were handed the shape of your hands. Think about a pie at a family table. There is one pie. Every slice taken is a slice gone, and everyone at the table knows it without a word being spoken. That silent arithmetic, the zero-sum table, is the oldest economics on Earth, and every wallet is a small pie. Even school agreed with the lesson. If you took a physics class, you learned conservation laws. Matter does not appear from nothing, energy is not destroyed, everything is bookkeeping. A closed room holds what it holds. It all fits together: the wallet, the instinct, the physics. What you have is what there is. So here is the strange part. Over the past few decades, some of the most careful measurements in the history of science, measurements of the oldest light in the universe, made by satellites floating 1 million miles from Earth, have been quietly pointing toward a possibility that breaks that lesson at the deepest level. Not bends it, breaks it. The possibility is this: space may not end. Not space is very big, not space is bigger than we can see. Space may literally run on forever, without an edge, without a wall, without a final shore. And if it does, if space is truly infinite and matter is spread through it the way our measurements suggest, then a very strange conclusion follows, almost against our will. Somewhere out there, unimaginably far away, but at a real, finite distance, there is another table, another coin, another you. And not one copy. If the reasoning holds, there are endlessly many. including versions of you whose lives took every turn yours could ever have taken. Versions who hold, by every accounting we know, everything. So how can that possibly be true? How do you get from a wallet on a table to endless copies of yourself scattered through space? Who measured what, and when, and how sure are they? That is the story of this video, and I will tell you now, honestly, that it ends at one of the sharpest open edges in all of science. Let's walk to it slowly, starting with the light. First, let's get the size of our room straight, because before you can ask whether space ends, you need to feel how far we can actually see. When you look up on a clear night, you are looking into the past. Light takes time to travel, so every star you see is a postcard from years ago, every galaxy a postcard from millions of years ago. Follow that logic to its limit, and you reach a hard boundary, the light that has been traveling since the universe's earliest days, arriving only now. Nothing from beyond that distance has had time to reach us. Not because nothing is there, but because the universe is not old enough for its light to have made the trip. Max Tegmark put the number on it. The most distant things we can now see are about 400 trillion meters away. And because space has been stretching while their light traveled, the full sphere of everything visible now spans roughly 93 billion light years. That sphere, everything any telescope can ever show us, every galaxy in every deep field photograph, is our Hubble volume. Remember the name, because it is about to become the basic unit of this story, the way a single parking space is the basic unit of a parking lot. And do not let the word unit shrink it in your mind. Inside that one sphere sit roughly 100 billion galaxies, each carrying on the order of 100 billion stars. We sit in one quiet corner of one of them, on a planet where the entire history of our species has played out under one sun among those billions of billions. Everything every human has ever owned, fought over, saved or lost, every wallet, every vault, every empire's treasury, fits inside this single parking space. Hold that, because the story we are walking into is about to treat all of it as one small unit in a large account. And notice what the boundary of that sphere is not. It is not a wall. Nothing changes there. No edge is drawn in space. It is a horizon, the same word sailors use, and for the same reason. Stand on a shore and the sea ends in a clean line. But no sailor ever believed the ocean stops at the line. The line is about your eyes, not about the water. Our cosmic horizon is exactly that, the limit of our view, with no reason whatsoever to be the limit of the world. So what lies past it? More of the same? Something different? Nothing at all? Hold the question, because the honest route to the answer starts somewhere unexpected, with the discovery of the oldest light in the universe, found by accident by two engineers who thought their antenna was broken. But the part of the story we need begins later, with a question that kept a young physicist awake, a question about why the universe is shaped the way it is. In 1978, a physicist named Robert Dicke gave a series of lectures at Cornell University, and in the audience sat a young postdoctoral researcher named Alan Guth. Dicke laid out a puzzle that most people outside physics had never heard of, called the flatness problem. To understand it, you need to know what physicists mean by the shape of space, and it is simpler than it sounds. Picture two ships leaving a harbour on perfectly parallel courses. On a flat sea, they stay the same distance apart forever. But the Earth is not flat, it is a sphere, so two ships sailing parallel north from the equator actually drift together and meet at the pole. The surface they travel on has a shape, and the shape decides what happens to parallel paths. Space itself is like that. In a universe with one kind of curvature, two parallel beams of light slowly converge, like those ships. In another, they slowly spread apart. And in exactly one special case, the perfectly flat case, parallel beams stay parallel forever. Here is what kept people awake. Every measurement kept coming back flat. Not roughly flat, suspiciously precisely flat. And flatness, it turns out, is an unstable balance, like a pencil standing on its point. If the early universe had been even slightly curved one way or the other, that tiny curvature would have grown ferociously as the universe expanded, and by now the universe would be either obviously curled up or obviously splayed open. For the universe to look this flat today, its curvature at the beginning had to be tuned to a precision that made physicists deeply uncomfortable. Nobody could explain it. It was simply how things were. Why does this matter for our coin? Hold on to one fact, because the whole video turns on it later. A perfectly flat universe, in the simplest reading of the mathematics, is not just balanced. It is infinite. Flat geometry, continued without interruption, has no edge to stop at. The flatness problem was not only a puzzle about balance, it was, quietly, a question about whether space ends. Alan Guth could not let the puzzle go. Through 1979, he worked at the Stanford Linear Accelerator Center, and in early December of that year, at home, late at night, he sat down with his notebook to work through a calculation about how the strange conditions of the very early universe might have affected its expansion. He was following a thread suggested by a colleague, Henry Tye, a routine-looking calculation, the kind a physicist does hundreds of times. Somewhere in that night's work, the routine calculations stopped being routine. Guth saw that if the infant universe had passed through a particular kind of high-energy state, a state physicists call a false vacuum, that state would not just sit there. It would drive space itself to expand at a runaway, doubling and redoubling rate, an exponential surge that could take a patch of space far smaller than an atom and swell it beyond all comprehension in less than a trillionth of a trillionth of a trillionth of a second. At the top of the notebook page, he wrote 2 words and drew a double box around them. Spectacular realization. What Guth had found that night would come to be called cosmic inflation, and the reason it electrified physics is that this one violent idea dissolved the flatness problem almost as a side effect. Think about blowing up a balloon. A small balloon is visibly curved. You can see the bend in its surface. Now imagine inflating that balloon until it is the size of the Earth. Stand on it, and the patch under your feet looks perfectly flat, the way a calm sea looks flat, even though the Earth curves. Inflation did that to space. Whatever curvature the universe was born with, that brief burst of exponential expansion stretched it so enormously that the part we can see, our entire visible universe, is just one tiny patch of something vastly larger, flattened by sheer stretching. The pencil didn't have to balance on its point, the stretching forced it flat. In 1981, Guth published the idea in the journal Physical Review, and cosmology reorganized itself around it. The reorganization was not instant, and it was not smooth. Guth's original version had a flaw he himself acknowledged, a problem with how inflation was supposed to end gracefully rather than tearing the young universe apart. Within a couple of years, in the early 1980s, other physicists, Andre Linde working one track, Andreas Albrecht and Paul Steinhardt another, rebuilt the engine with the flaw repaired, in versions called new inflation and later chaotic inflation. The repaired engine worked beautifully, and decades later the field's regard for the idea was made official when Guth received the Kavli Prize in 2014, one of physics' highest honors, for pioneering the theory of cosmic inflation. But hidden inside those repairs, physicists had already begun noticing something odd about the engine, a feature, not a flaw, that refused to go away, and that we will meet properly in a few minutes, because it is the feature that makes this whole story enormous. But first, notice what the balloon picture quietly implies, because this is where our story tips toward the strange. If everything we can see is one small, flattened patch of something enormously larger, then what is the rest? How much more is out there, beyond the farthest thing our telescopes can reach? And is more even the right word, or does it just keep going? Before we can answer that, we need to meet the light I promised, because an idea this large is worthless until something you can measure agrees with it. Inflation made a very specific, testable promise, and the test would come from the oldest light in existence. It is worth pausing to say what the universe's ordinary history means after inflation hands over the keys, because the handoff is the bridge between the strangest physics and the world you can see out a window. When inflation ends in a region and its energy floods out as hot particles and light, what follows is a long, patient cooling. The flood thins as space keeps stretching and the simplest atoms condense out of the glare. Then gravity, slow, relentless, working from those faint density ripples, begins gathering matter into the first stars, then galaxies, then everything the deep field photographs show. The ancient glow we are about to meet is the light released early in that cooling, stretched by billions of years of expansion into faint microwaves filling every direction of the sky. Point any sufficiently sensitive detector upward, anywhere on Earth, and it hums with light older than every star. That hum is where the evidence lives. Here is the promise in plain terms. Inflation says the universe was stretched from something almost unthinkably small. But the quantum world, the world of the very small, is never perfectly still. It trembles. Tiny random fluctuations flicker constantly at the smallest scales, and during inflation, those microscopic trembles got caught in the stretching and blown up to cosmic size, like a whisper amplified into a roar. Those stretched trembles became slight variations in the density of matter, a little more here, a little less there. And everywhere there was a little more, gravity had something to grab. Over billions of years, those slightly denser spots pulled in material and grew into galaxies. The theory made a promise you could check. The early universe should carry faint ripples at a level of roughly 1 part in 100,000 printed across the sky. And there is a place to look for that printing. The universe's baby picture still hangs in the sky, in every direction, in the form of a faint glow of microwaves, the leftover light of the hot young cosmos, released before any star existed and traveling ever since. Physicists call it the cosmic microwave background. If inflation was right, that glow should not be perfectly smooth. It should carry the ripples. On the 18th of November, 1989, NASA launched a satellite called COBE, the Cosmic Background Explorer, to photograph that glow with a precision no one had ever attempted. A team of about 40 scientists, led on this measurement by an astrophysicist named George Smoot, then spent more than 2 years hunting through its data for ripples 100,000 times fainter than the glow itself. Smoot described the job as like listening for a whisper during a noisy beach party. That is not a figure of speech invented for television. That was the actual working condition. The signal they needed sat beneath the hum of our own galaxy, beneath the noise of the instruments, beneath almost everything. Before the ripple hunt could even begin, COBE had to answer a simpler question. Was this ancient glow really what the theory claimed? The cooled-down light of a hot young universe. One of the satellite's instruments, led by John Mather, measured the glow's spectrum, its exact mix of intensities across wavelengths, and the result became one of the most famous graphs in science. A glow left over from a hot, dense past should have a very particular spectral shape, and COBE found that shape matched to within about 50 parts in a million. The most perfect example of that thermal signature ever measured anywhere by anyone. The temperature came out at 2.725 degrees above absolute zero, steady across the whole sky to about 1 part in 100,000. Picture inspecting a painted wall the size of the sky and finding its color uniform to 1/100th of a thousandth, and then being asked to find the brushstrokes anyway. Those brushstrokes were the ripples Smoot's team was after. At 4 minutes past 8 on the morning of April 23, 1992, at a physics meeting in Washington, D.C., Smoot's team announced what they had found. The whisper was there. Ripples at 1 part in 100,000, right where the theory said to look. The room understood immediately what it was seeing, the seeds of every galaxy that would ever form, and a fingerprint left by whatever stretched the universe in its first instant. The announcement made front pages around the world, and it eventually brought Smoot and his colleague John Mather the Nobel Prize. Between COBE and the story's next chapter came a steady tightening of the picture. A follow-up NASA mission called WMAP spent most of a decade sharpening the map of the ancient glow, turning COBE's blurry 7-degree smudges into crisp detail. It pinned down the universe's basic numbers, its age, its ingredients, its geometry, to a precision cosmologists a generation earlier would not have believed possible. Cosmology, long teased as the science where the error bars were as big as the results, was becoming a precision discipline. And precision is exactly what our question needs, because is space flat is a question that lives or dies in the decimal places. 2 decades later, a European satellite named Planck, launched in 2009, parked 1 million miles from Earth, staring at that same ancient glow with exquisite instruments, turned the whisper into a full recording. Planck measured the ripples across the entire sky and checked their statistical fingerprint in detail against inflation's predictions. The patterns matched. And Planck measured something else, the number this whole video pivots on, the shape of space. Remember the ships and the parallel light beams? Planck could perform a version of that test across the largest distances light has ever traveled, using the ripple pattern itself as a ruler. The verdict? Space is flat to within less than half of 1%. Within the precision of the best instruments our species has ever built, the universe has no detectable curve at all. And Planck's agreement with inflation went beyond the amount of rippling. The theory predicts a specific personality for the ripples, in plain terms, that they should be very nearly the same strength at every size, but not exactly. Tilted, ever so slightly favoring the largest scales. Planck measured the tilt, and it was there, small and clean, sitting almost exactly where the simplest inflation models put it. The ripples also carried the statistical texture the theory demanded, the particular kind of randomness a stretched quantum tremble should have. One predicted signature is still being hunted. Inflation should also have shaken spacetime itself, printing a faint swirl into the ancient light, and experiments with names like Bicep and Keck sit on the South Pole ice, straining to find it. So far, not seen, only bounded. If that swirl is ever found, it will be the closest thing to a photograph of inflation in the act. Its absence so far is the honest asterisk on an otherwise remarkable scorecard. Now stop and feel where we are standing, because this is the hinge of the whole story. Flat was the geometry that, continued without interruption, has no edge. Our best measurement of the real universe says flat as far as precision can reach. And the mechanism that explains the flatness, inflation, independently explains the ripples in the right amount with the right fingerprint. The pieces agree with each other. So does that mean space is infinite? Does the measurement prove there is no final shore?
No, and I want to be completely straight with you about this, because this is exactly the kind of moment where a video can quietly lie to you, and this channel does not do that. Flat is consistent with infinite. It is what an infinite universe would look like, but it is also what a finite universe would look like if that universe was stretched large enough. The Earth-sized balloon again. Flatness is measured. Infinity is an inference. Max Tegmark, a physicist at MIT whose name will anchor the rest of this story, puts the honest version this way. We accept the existence of things we cannot see but could see if we moved or waited, like ships beyond the horizon. Beyond the farthest light we can receive, there is almost certainly more universe. The measurements genuinely do point that way. How much more is the open question? The simplest reading of a flat universe says, it does not stop. Hold that thought exactly as it is. Flat is measured, infinite is the simplest reading, and the two are not the same claim. Everything that follows hangs from that distinction, and we will come back to it at the very end. Because here is the next question, the one that turns a measurement about geometry into a story about you and your coin. Suppose the simplest reading is right. Suppose space really does run on without end. Endless room, endless matter, the same physical laws everywhere. What happens then?
What does an infinite amount of space actually do? The answer was worked out with real care, and it runs through one of the strangest and most wonderful arguments in modern physics. It starts with a question that sounds almost childish. In all that endless space, how many different ways can things be arranged? The person who followed that question all the way down is Max Tegmark. Born in Stockholm in 1967, trained in Berkeley, now a professor at MIT, Tegmark is the physicist who took the loose talk of other universes and organized it into a careful hierarchy. 4 levels, each stranger than the last, each resting on different assumptions. It is worth 30 seconds on the whole ladder, because knowing what we are not talking about keeps this story honest. Level 2 in his scheme is the collection of other pocket universes budded off by inflation, where even the constants of physics might differ. Level 3 is the many worlds reading of quantum mechanics, realities branching not far away in space, but alongside us, in the abstract space of quantum possibilities. Level 4 is Tegmark's own most radical idea, the one he admits puts him in a minority and that he was warned would damage his reputation and career. The hypothesis that every consistent mathematical structure exists physically. You do not have to accept any of those tonight. Our story lives entirely on the first level, the most conservative rung, the one Tegmark calls a generic prediction of the standard picture of cosmology. And it is exactly the endless flat space we have been describing. He named it the Level 1 multiverse, not other dimensions, not ghostly parallel realities layered on top of ours. Just this universe, our laws, our particles, our kind of space, continuing past our horizon without end. Other regions of the same space we live in, so far away their light has never had time to reach us. Mark the difference well, because it is the difference between science fiction and a counting argument. Quantum many worlds live in an abstract elsewhere. Level 1 copies live here, in ordinary space, in the same universe as your coffee cup, just farther away than light has yet had time to cross.
Why does this matter so much to him? Because Tegmark's insight was that the vague question, are there other universes, becomes a precise question the moment you make it about counting, and counting is something physics is genuinely good at. Not could there be another you, which invites shrugs, but how many distinct ways can a region of space be arranged, and how many regions are there? Turn the metaphysics into arithmetic, and the arithmetic will tell you things whether you like them or not. To understand what endless space does, Tegmark asks you to count. Take a region the size of everything we can see, our entire visible universe. Physicists call a region that size a Hubble volume, a sphere roughly 93 billion light-years across, holding everything any telescope can ever show us. It feels infinite. It is not. Count the protons in it, the basic building blocks of ordinary matter, and you get a definite number, about a 1 followed by 80 zeros. Enormous, but finite. Now ask a sharper question. How many different ways could matter possibly be arranged inside a region that size? Not just the arrangement we see, every arrangement physics allows. Every possible position of every possible particle. Here is the analogy that makes the answer graspable. Think about license plates. A plate has a fixed number of characters, and each character has a fixed set of options, so there is a fixed, countable number of possible plates. A big number, but a number. A Hubble volume works the same way. Because it holds a finite amount of matter and energy, the rules of quantum physics allow it only a finite menu of distinct states. The number is beyond astronomical, roughly a 1 followed by 10 to the power 115 zeros, a number so large that writing its zeros would itself require more space than our visible universe contains. But it is finite. The menu has a last page. Now put the two facts side by side and watch what happens. Fact 1. A region the size of our visible universe can only be arranged in finitely many ways. Fact 2. If space is infinite, there are infinitely many such regions. Finitely many possible plates. An endless parking lot. What must happen? Plates must repeat. That is the whole argument. Let it land one piece at a time,
because each piece alone is easy, and the shock lives only in their combination. Piece 1. Our region holds a finite amount of stuff, measured, ordinary, uncontroversial. Piece 2. Finite stuff means finitely many possible arrangements. That is quantum physics doing what it always does, putting a flaw under how finely the world can differ. Piece 3. Infinite space means infinitely many regions. That is just the flat geometry, read simply. No single piece asks you to believe anything wild. Stack them, and the wildness assembles itself. In an endless space built of finitely arrangeable regions, arrangements must recur. Somewhere out there, if the assumptions hold, there is a region arranged almost exactly like ours. And somewhere much farther, one arranged exactly like ours, down to every particle. Another Milky Way, another Sun, another Earth. Another table, another coin, another you, pausing this very video at this very moment. Notice too what the argument does not require. It does not require anything to have arranged the copies, coordinated them, or known about them. No signal passes between the regions. No mechanism places the duplicates. The repetition is forced by arithmetic alone, the way a long enough book must reuse words, not because anyone planned the reuse, but because the dictionary is finite and the book is not.
Where does an idea like arrangements must repeat even come from? It is older than cosmology, older than the discovery of galaxies. In the 1870s, the Austrian physicist Ludwig Boltzmann was wrestling with a different puzzle entirely: how the disorderly jostling of atoms produces the orderly laws of heat. In the middle of that work, he coined a word, ergodic, for a system that, given enough time, wanders through every state available to it. Shuffle a deck of cards over and over, forever. The deck has a huge but finite number of possible orders, so with endless shuffles, every order must eventually appear and reappear endlessly. That is ergodicity in a sentence. Finite possibilities plus unlimited sampling equals total repeated coverage. For decades, it remained a working assumption of physics rather than a theorem, until the early 1930s, when the mathematicians John von Neumann and George Birkhoff finally proved rigorous versions of it, pinning down exactly when the shuffle really does visit everything. What Tegmark's argument does is take Boltzmann's shuffle and hand it to the universe. The deck is a Hubble volume, and the orders are its possible quantum states. Then comes the key swap. Instead of shuffling one deck through endless time, infinite space deals endless decks all at once. Sampling across space replaces sampling across time. Same theorem, cosmic table. There is one more assumption hiding in that argument, and honesty requires we drag it into the light. Repetition needs more than infinite space. It needs matter to actually explore the possibilities, rather than repeating one dull pattern forever, like wallpaper. An endless parking lot where every car has the same plate breaks the argument. The technical name for the needed ingredient is ergodicity, the idea that across enough space, matter genuinely samples all its possible configurations. Is that true of our universe? Here the story loops back on itself beautifully. The ripples COBE heard and Planck mapped are the evidence. Those ripples were seeded by random quantum trembling, and random is exactly the property needed. Inflation, the same mechanism that flattened space, also dealt every region its own random starting hand. Tegmark's phrase for it is that inflation generates an ergodic random field. In his words, everything that could in principle have happened here did in fact happen somewhere else. The dice that rolled our region rolled every region, and infinite rolls of honest dice leave nothing untried. So the chain is complete, and you should see both its strength and its hinges. Measured, space is flat to 0.5%, and the ripples match inflation's fingerprint. Inferred, flat space, read simply, runs on forever. Assumed, matter explores its possibilities the way the ripples suggest. Concluded, every possible arrangement of a universe-sized region, every possible arrangement, exists somewhere
and not once, but endlessly. Sit with the size of that conclusion for a moment. This is the part I find hard to stop thinking about. Not that another you might exist, but that the argument for it is this short. A measurement of geometry, a counting rule from quantum physics, and one page of logic. That is the entire distance from your coin on the table to endless copies of everything.
How far away are these copies then, can we say? Tegmark did the arithmetic, and the numbers are the largest you will ever hear attached to a real physical claim. For a copy of you, just you, not the whole neighborhood, matter would need to repeat an arrangement the size of a person. The distance his estimate gives is 10 to the power of 10 to the 29 meters. I need to pause on what that means, because it is not a number in the ordinary sense. 10 to the 29 is a 1 with 29 zeros. 10 to the power of that is a 1 followed by that many zeros. So many that if you tried to write the zeros themselves, 1 per atom, the atoms of our entire visible universe would run out long before the zeros did. For a perfect copy of our whole Hubble volume, every galaxy, every star, every person, every coin identical, the distance grows to 10 to the power of 10 to the 115 meters. These are distances that make the width of our visible universe, those 93 billion light-years, into something indistinguishable from zero. And yet, and this is the point that matters, they are finite. The nearest identical you is not infinitely far away. It is a definite distance away, just one written in a notation our minds were never built to feel. Let me try to give those distances something to stand next to, because the mind slides off double exponents like water off glass. Inside just our region, the one Hubble volume we can see, Tegmark counts at least 100 billion habitable planets, a 1 with 20 zeros in our neighborhood alone. The largest structures astronomers have ever mapped, great walls and filaments of galaxies, top out around scales of 1 trillion meters, and beyond that size the universe goes smooth, the same porridge everywhere, exactly as the repetition argument needs. Now climb the ladder of copies. The nearest copy of you, 10 to the 10 to the 29 meters. The nearest copy of a full sphere 100 light-years wide. You, every star you can see with your naked eye, every radio signal humanity has ever leaked into space, all duplicated at once. 10 to the 10 to the 91 meters. The nearest copy of the entire observable universe, 10 to the 10 to the 115. And here is the detail that makes the ladder feel real rather than mystical. The rungs are not arbitrary. Each one is set by pure counting. The bigger the region you want duplicated, the more possible arrangements it has, so the farther you must travel before the deck deals it again. The universe is not hiding your copies out of shyness. The spacing is arithmetic. And between you and your perfect copy, the same counting fills the gap with something more intimate, the near copies. Far closer than the perfect duplicate, though still absurdly far, are versions built from almost your arrangement. A you that turned left where this you turned right. A you whose life matches yours to yesterday and diverges this morning. The counting argument prices variation. Small differences are cheap and therefore near. Perfect identity is expensive and therefore far. Which means the copies are not one twin at one distance. They are a continuous fog of yous, thickening with distance, every possible version realized somewhere on the ladder. Including, since arrangements of ownership are just arrangements of matter, the versions the title of this video promised. The ones for whom the divergence came at exactly the right moment, and everything landed in their hands. Here's the strange part, and it deserves its own breath. Nothing about those copies is speculative physics in the usual sense. No new particles, no new forces, no new dimensions. And the people saying it are not fringe voices, they're the architects of the field itself. Alexander Vilenkin, a cosmologist at Tufts University, is one of the physicists who discovered eternal inflation in the first place, working through its mathematics back in the 1980s. He has lived with this picture longer than almost anyone alive. In his book, Many Worlds in One, from 2006, he wrote the conclusion plainly and without flinching. Countless identical civilizations are scattered in the infinite expanse of the cosmos. Somewhere, he writes, there are remote planets inhabited by identical creatures, including, in his own word, our clones. Not similar beings, clones, particle for particle repeats of us, dealt by the same shuffle that dealt this room. And Alan Guth, the same Alan Guth of the Notebook and the Double Box, summarized the logic of an eternally inflating universe in one sentence. Anything that can happen will happen. In fact, it will happen an infinite number of times. When the person who lit the fuse and the person who mapped the explosion both read the mathematics the same way, the idea has earned the right to be taken seriously. And taken seriously is exactly what we are doing tonight. Seriously enough to honor it, and seriously enough to stress test it before we are done. That word, eternally, is one we have not fully earned yet. Because I told you inflation happened once, at the beginning, and stopped, that is only half the story, and the other half is where this picture gets its true scale. When physicists followed inflation's mathematics to the end, several of them, Vilenkin, the Russian-American physicist Andrei Linde, and others, kept finding the same unsettling feature. Inflation is easy to start and almost impossible to finish. Picture bread dough rising, with gas pockets forming inside it. This is Tegmark's own image. Each pocket is a region where inflation has ended, where the violent stretching has stopped, and the energy has poured into ordinary matter and light, a pocket universe, ours among them. But the dough between the pockets keeps rising, and here is the key. It rises faster than pockets form. The inflating dough always outruns its own bubbles. Once inflation begins anywhere, the total volume of inflating space grows without limit, budding off pocket universes forever. Why should inflation be so hard to stop? The mechanism is worth 2 minutes because it is one of the most beautiful pieces of reasoning in the story. The engine of inflation is a field. Physicists call it the inflaton, and its behavior is like a ball on a long, gentle hillside. While the ball sits high on the slope, its energy drives the runaway stretching. When it finally rolls down into the valley, the stretching stops, and the stored energy pours out as a flood of hot particles and light, the event physicists call reheating, the true beginning of our universe's ordinary history. Left alone, every region's ball would roll downhill and inflation would end everywhere. But nothing quantum is ever left alone. The same restless trembling that seeded the galaxies also jiggles the ball itself, and in some regions, the random jiggle kicks it back up the slope. Here is the devastating arithmetic. The regions where the ball got kicked up keep inflating, and inflating space multiplies itself exponentially. So even if uphill kicks are rare, the rare regions that get them balloon so enormously that they dominate everything. Downhill regions become pocket universes. Uphill regions become factories for more space, which sprouts more pockets and more factories. Run the logic forward and it never closes. Somewhere, always, a ball is being kicked uphill, and the dough rises forever. Physicists call this eternal inflation, and among those who study the early universe, it is a mainstream expectation, though Guth himself is careful to say there is no clear consensus, only that to many of us the assumptions seem to be pointing that way. If it is right, then the endless space of our story is not even the whole of it. Our infinity is one pocket in a dough that never stops rising, one universe in a structure that manufactures universes without end. And the other pockets may not even resemble ours. In Tegmark's hierarchy, those sibling bubbles are the level 2 multiverse, where the settling out of each pocket could freeze different constants of physics into place, the way water can freeze into different crystal patterns depending on how the freeze happens. Our story needs none of that tonight. Level 1, plain, endless space, our own laws,
is already enough to put a copy of you at a computable distance.
And eternal inflation hides one more wonder. So strange, it sounds like a trick until you see what it means. You might object, if our universe began as one bubble in the dough, one pocket formed at one moment, surely it must be finite. A bubble has a wall. A wall encloses a finite volume. How could an infinite universe fit inside a finite bubble? And yet the mathematics, worked out by physicists including Martin Bucher and David Spergel in the late 1990s, says it can. From the outside, the bubble looks finite, a growing pocket in the dough. But space and time are not carved up the same way for someone inside as for someone outside. And viewed from within, the bubble's own geometry opens out into an endless space, an infinite interior wrapped in a finite skin. I still find this genuinely strange, in the best way. Our whole endless universe, copies and all, may sit inside something that, seen from without, is merely one bubble among endlessly many. Before we cash the title's promise, one question deserves a straight answer, because everything hangs on it. What is wealth, physically? Strip away the feelings and look at what money actually is as an arrangement of matter. A gold bar is a particular stack of atoms in a vault. A bank balance is a particular pattern of electrons in a machine's memory. A deed, a contract, a fortune, each is, at bottom, a configuration. Matter arranged one way rather than another, plus minds arranged to agree on what the pattern means. There is no additional substance called wealth hiding behind the arrangements. The arrangements are the whole thing. Why does this matter? Because the counting argument we built cares about exactly one thing: arrangements. It does not know or care which patterns humans find precious. It simply guarantees, given its premises, that every physically possible pattern occurs endlessly. The pattern in which a vault the size of a building stands filled. The pattern in which the ledgers of a world agree that one person holds title to a star system. The pattern in which that person is, particle for particle, you. Improbable? Wildly. But improbable is a statement about frequency, not possibility. And in an infinite ergodic universe, everything possible is mandatory. Rare patterns are not excluded. They are merely spaced farther apart on the endless shelf. So let us return, finally, to the coin, because we have now earned the sentence this video's title made, and we can say it with its full weight and its honest conditions. In this picture, flat space read as infinite, seeded the way the ripples suggest. Every arrangement of matter that physics allows exists somewhere, infinitely often. And every arrangement is not a poetic phrase. It includes, by sheer counting, the arrangements you care about. Somewhere, a version of you looked at the numbers in your bank account and saw them larger by 1 digit. Somewhere, larger by 10. Somewhere, because nothing in physics forbids it, a version of you owns the deed to a star system, not as fantasy, but as one legal arrangement of matter among the endless arrangements an infinite universe is obliged to contain. Wealth, in the end, is a configuration, a particular pattern of atoms in vaults, of electrons in bank ledgers, of neurons in the minds that agree the pattern means ownership. And in an infinite ergodic universe, every configuration is realized. Scarcity, the iron law your wallet taught you, turns out to be a local rule. True in any one region, the way there is only one of you is true in any one region. False in the largest accounting, if the accounting truly has no end. Why does this matter if the copies are forever out of reach?
That is exactly the right objection, and the rest of this video belongs to it. Because the same physics that gives this abundance with one hand takes it away permanently with the other. And what it leaves behind is stranger than either. Start with the wall. Every one of those other regions is receding from us, not moving through space, but carried by space itself as it stretches. And for the most distant regions, the stretching adds up faster than light can cross it. Picture two rowboats on an ocean, rowing toward each other, while the water between them widens faster than either can row. They are not slow, the ocean is simply winning. That is our situation with respect to the copies. How do we know the ocean is winning? Because of a discovery that shocked astronomy less than 30 years ago. The stretching of space was expected, but everyone assumed gravity must be gradually slowing it, the way a ball thrown upward slows. In 1998, two rival teams of astronomers set out to measure exactly how much the expansion was slowing, using distant stellar explosions as standard beacons. Both teams found the same impossible answer. It is not slowing at all. It is speeding up. Something, nobody knows what, pushes the expansion faster, and it was given the placeholder name dark energy. The idea itself had a strange pedigree. Back in 1917, Einstein had inserted an extra term into his own equations to keep the universe static, a term he came to regret. The 1998 discovery resurrected a version of that very term as the simplest description of the push. Its measured strength is one of the most uncomfortable numbers in physics. In the natural units theorists use, it is absurdly, almost insultingly tiny. A 1 pushed 123 decimal places down, and yet not zero. That whisper of push, compounded across billions of light years, is what widens the water between the rowboats. If that acceleration continues, the wall is not temporary. Regions beyond a certain distance are not hard to reach. They are unreachable in principle. Tegmark notes you would never get there even traveling at the speed of light forever. The abundance is real in the model, and the model itself guarantees you can never touch it. No signal, no ship, no message can ever pass between you and the version of you who has everything. The universe in this picture is the one bank that provably exists and provably cannot be robbed, visited, or even written to.
Follow the acceleration far enough forward, and it turns melancholy in a quiet, majestic way. The distant galaxies we can currently see are, one by one, being carried over the edge of reachability. Simulations of the far future, around 100 billion years from now, show our night sky reduced to a single island. It is the merged remnant of the Milky Way and our neighbor Andromeda, a pairing astronomers have nicknamed Milkdromeda, alone in a darkness that was once crowded with galaxies. Observers alive then, looking out with any instrument, would find no evidence that other galaxies ever existed. Their measurements would honestly report a small, lonely universe, which should make you wonder, in the other direction, what our own horizon might already be hiding from us. Sit with that for a second, because it is quietly one of the most humbling thoughts in all of cosmology. Those far future astronomers of Milkdromeda would not be careless or foolish. They would build magnificent instruments, survey their sky with perfect rigor, and conclude, honestly from flawless data, that the universe is one galaxy in an empty dark. Every measurement would confirm it, and they would be wrong, not through any failure of method, but because the evidence itself had left the building before they were born. Now turn the telescope around. We are also observers, at one cosmic moment, drawing conclusions from the light that happens to still be reachable. What has already been carried past our wall? What conclusions are we drawing, honestly and rigorously, from a sky that has already forgotten something? There is no answer to that question. That is precisely the point. The strange part is that our sky, too, is a room with walls we cannot see past, and we have no way to know what the walls have already stolen. Now, an honest aside about the discovery that revealed the acceleration, because the human story deserves its beat. Those two rival teams in 1998 were not friendly collaborators. They were competitors, racing each other across the same sky, each fully expecting to catch the universe slowing down. Competition is exactly what makes their agreement so convincing. When two groups that would love nothing more than to prove each other wrong arrive at the same impossible number, the number has earned attention. Within a few years, the impossible became textbook, and the discovery received the field's highest honors.
That is worth remembering when tonight's more speculative ideas feel dizzying. This same field, in living memory, met a result nobody wanted, fought it, verified it, and rebuilt cosmology around it. The system that vets these claims has teeth.
There is a second thing the copies quietly steal, and this one is stranger. They steal certainty about your own future. Physics, since Newton, held out an ideal. Know the present perfectly, and the laws will tell you the future perfectly. In a universe with copies, that ideal dies for the gentlest possible reason. Suppose you knew the state of the entire cosmos, every particle. You would then know that there are endlessly many regions containing an observer exactly like you, having exactly this experience, remembering exactly this life. Some of those observers are about to have different things happen to them. Their regions differ, far away, in details that will arrive at different times. Now answer one question. Which of them are you? There is no answer. Nothing in physics distinguishes you from them. That was the whole point of identical. So even with perfect knowledge, your own future becomes a matter of probabilities. Most of my copies experience this, few experience that. Determinism dies not with an explosion but with a shrug, not because the laws fail, but because you turns out to name endlessly many beings at once, whose stories are about to diverge. Let me make that concrete because it sounds abstract and it is actually about tomorrow morning. Picture the moment your alarm goes off. In this picture, that moment is being lived, right now in the timeless accounting of an infinite universe, by an uncountable crowd of observers in your exact situation. Same room down to the dust, same memories down to this video, same hand reaching for the same phone. For most of them, the day that follows will match yours in every detail. But the regions are not perfectly synchronized forever. Tiny differences, far away in each region's surroundings, eventually reach in. For some of that crowd, today is the day the difference arrives. The unexpected call, the chance meeting, the small accident, good or bad. Before the divergence, there is no fact about which member of the crowd you are. You is the whole crowd. After it, the crowd has split, and each branch says I with perfect sincerity. So when you wonder what tomorrow holds, the physics of the level 1 multiverse gives this strange, precise answer. Tomorrow holds everything, distributed across the crowd that is you, and your uncertainty about your own future is not ignorance of a hidden fact. It is the honest arithmetic of being many. And the counting argument has one more resident, the strangest tenant in this whole endless building. If arrangements of matter recur, then among the arrangements that must occur somewhere is a very unsettling one. Picture a bare, momentary brain, assembled not by birth and life, but by sheer random fluctuation. Complete with false memories of a life never lived, convinced it is sitting somewhere watching a video about the cosmos. Physicists call these hypothetical observers Boltzmann brains, after the same Ludwig Boltzmann of the shuffled deck, who explored fluctuation ideas in his own century. In certain far-future scenarios, such randomly assembled observers could even come to outnumber ordinary ones. Physicists treat that not as a delightful twist, but as a warning light. Any theory that predicts most observers are deluded fluctuations has a problem, because it quietly undermines every measurement those observers trust. Nobody believes you are a Boltzmann brain. The point is sharper. A theory of infinite recurrence has to be handled with care, or it starts to eat its own evidence. And there is a lovely historical symmetry buried here. Boltzmann himself, back in his own century, wondered whether our entire orderly universe might be nothing but a rare, temporary fluctuation in an otherwise disordered cosmos. His era's version of the recurrence idea, dreamed up decades before anyone knew other galaxies existed. The 19th century asked it about time. Given forever, must order recur? The 21st asks it about space. Given endlessness, must order repeat? Same question, rotated 90 degrees, and still, honestly, open.
By now, a fair-minded viewer should be feeling a pressure building, and I want to voice it rather than smooth past it. This all sounds a little too easy. Infinite everything, endlessly repeated, and conveniently, none of it observable? Is this physics, or is it a very sophisticated bedtime story? That doubt is not a layman's error. It is shared, loudly, by serious physicists, and the honest second half of this story is the fight over exactly that question. The sharpest critic has been George Ellis, a South African cosmologist of enormous standing. He wrote one of the field's foundational books alongside Stephen Hawking, which makes his dissent impossible to wave away as outsider grumbling. Ellis has been prosecuting this case for years, in journal articles with titles as blunt as "Opposing the Multiverse." His objection is not that the multiverse is weird. Physics is routinely weird. Nobody abandoned quantum mechanics for being strange. His objection is procedural, and it cuts at the root. The multiverse may not be testable, even in principle, and testability is not an optional courtesy in science. It is the border of the discipline. Every claim we have celebrated tonight earned its place by surviving a possible execution. Inflation predicted ripples that COBE could have failed to find. The flatness verdict could have come back curved. What observation could the level 1 multiverse fail? What measurement, even in imagination, comes back reading no copies? In the journal Nature, in 2011, Ellis put his conclusion without cushioning. No direct observational test of the hypothesis is possible, and scientists, he warned, are beginning to confuse science with science fiction. His deepest point is about infinity itself. Even a universe fully open to our instruments could never be verified as infinite, because counting an infinite number of objects takes an infinite amount of time. Infinity, Ellis argues, is not a measurement anyone will ever make. It is always an extrapolation, a smooth continuation of what we see into what we cannot.
The defender's reply is worth hearing in its strongest form, because this is a genuine argument between serious people, not a demolition. They point out that science routinely accepts unobservable consequences of well-tested theories. Nobody has visited the interior of a black hole either, yet we treat the predictions of the equations that describe them as physics, because the equations earn trust where they could be tested. Inflation, the defenders say, is exactly such a theory, tested against the ripples, the flatness, the tilt. And the level 1 multiverse is not an added hypothesis, but an unavoidable consequence of taking the tested theory at face value. You do not get to keep inflation's successes and quietly delete its implications. To which Ellis, in essence, answers, a consequence you can never check is precisely where taking a theory at face value must stop. Both positions are coherent. What separates them is a philosophical judgment about where physics ends, and that judgment itself is not something any satellite can measure.
And the doubts are not only philosophical. The measured ground under this story has real cracks, and you deserve to see each one. Crack number 1. The flatness itself has a dissenting reading. In 2019, 3 cosmologists, Eleonora Di Valentino, Alessandro Melchiori, and Joseph Silk, published a paper in Nature Astronomy pointing at a subtle feature of the Planck data. They argued it fits better with a universe that is slightly closed, curved in on itself like a sphere, and therefore finite. A finite universe has finitely many regions, and the entire copies argument collapses. There is even a small human twist buried in that dispute. Joseph Silk, arguing for the finite universe, was the doctoral advisor of Max Tegmark, the man whose name is attached to the infinite one. Other cosmologists pushed back hard, arguing that when all datasets are combined, the flat reading wins comfortably. But the episode is a live reminder that 0.5% of uncertainty is where an infinity can hide. Crack number 2. Flat does not even force infinite. Space could be flat and still finite if it wraps around on itself, the way an old video game screen wraps, where walking off the right edge returns you on the left. Astronomers searched the microwave sky for the telltale repeated patterns such a wraparound would print, matching circles in the ancient light, and found none. The universe is not wrapped tightly enough to catch, but wrapped too largely to see? That cannot be ruled out. Crack number 3 cuts deeper. In a universe where everything happens infinitely often, probability itself starts to wobble. What does it mean to say one outcome is more likely than another when both occur an infinite number of times? Physicists call this the measure problem, and it is not a pedantic quibble. The theory's own predictions depend on how you tame the infinities, and rival taming schemes give different answers. The physicists working on it have proposed rival rulebooks for taming the infinities, schemes with names like the proper time cutoff, the scale factor cutoff, the causal diamond measure, the stationary measure, each a different way of drawing a finite sample from an infinite population before comparing outcomes. Picture trying to determine whether a bottomless jar holds more red marbles than blue. You cannot count them all, so you scoop a sample, and then discover, to your horror, that the answer depends on the shape of your scoop. Scoop one way, red wins. Scoop another way, blue. That is the measure problem in a sentence. In an infinite universe, the theory's predictions depend on the sampling rule, and the theory itself does not tell you which rule is right. Ken Olam, a cosmologist who works on exactly this, wrote with admirable bluntness that the problem of defining sensible probabilities in eternal inflation seems not to be solved. And crack number 4 reaches all the way back to the beginning. In 2003, Arvind Borde, Alan Guth, and Alexander Vilenkin proved a theorem showing that an eternally inflating universe cannot be extended infinitely into its own past. The process must have had some kind of beginning. The theorem is purely about the geometry of expansion and says nothing about what the beginning was. Recent work has even constructed possible exceptions, so its reach is still being argued. But it opens a genuine tension inside the picture. If the past is finite, then the pocket universes made so far may number finitely many. And already infinitely many copies becomes a claim about the unending future rather than the present. Even the experts, you notice, are counting on their fingers here.
So where does the field actually stand? Somewhere refreshingly honest, if you listen closely. The physicists who built this picture defend the reasoning and freely admit the hinges. Guth: no clear consensus, but the assumptions seem to point this way. Tegmark: the level 1 multiverse is the generic prediction of the standard model of cosmology, while granting that what is measured is flatness and what is claimed is more. Ellis and the skeptics: extrapolation is not observation, and infinity may never be sciences to certify. This is not a scandal. This is what the edge of knowledge looks like while the workers are still on it. And the ground can still move. It moved recently, on the 19th of March 2025, at a physics meeting in Anaheim, California. A project called DESI, the Dark Energy Spectroscopic Instrument, runs on a telescope in Arizona and has measured the positions of tens of millions of galaxies, tracing the influence of dark energy across 11 billion years of cosmic history. That March, its team reported hints that dark energy, the engine of the accelerating expansion, may not be constant after all. The data lean toward a push that is weakening today. The statistical strength sits below the field's 5 sigma discovery threshold, a hint, not a finding, and some analyses argue it may yet dissolve into subtleties of the supernova datasets. But the stakes are hard to overstate. As DESI's director Michael Levi put it, whatever the nature of dark energy is, it will shape the future of our universe. Will Percival, one of the project's spokespeople, said the simplest explanation for what we see is shifting. Evolving dark energy seems promising. And one of the project's cosmologists told a reporter that possibilities long considered closed, including a far future where expansion someday reverses into collapse, are now back on the table, strictly a speculation.
If the push weakens, the walls between the regions, the permanence of the separation, even the far future of the whole endless structure, all of it keys to a number we have not finished measuring. As Andrei Kucho, one of the DESI researchers, said, maybe the universe is telling us it's more complicated than we thought it was. So is the question hopeless then, permanently stuck? Not quite, and this distinction matters. The premises of the argument are measurable even if its conclusion is not. That is where the real action is, and it is worth knowing exactly what future data could move this story in either direction. Watch 3 dials. Dial 1, curvature. The flat versus closed dispute lives inside 0.5% of measurement uncertainty, and the next generation of sky surveys, instruments now mapping galaxies by the tens of millions, will tighten that number. If curvature comes back decisively closed, the infinite universe dies by measurement, copies and all, and this video gets a sequel with the opposite title. Dial 2, topology. Sharper maps of the ancient light allow deeper searches for the wraparound patterns of a flat but finite universe. Silence so far, but the search has limits that can still be pushed. Dial 3, dark energy. DESI's hint, if it hardens into a discovery, rewrites the far future, the walls, the horizons, the trajectory of the whole structure. 3 dials, all physically real, all being read right now by working instruments. The multiverse itself may be forever past the horizon. The case for it and against it is being weighed in laboratories this decade. That is not stuckness. That is science operating exactly at its own edge, which is where this channel likes to stand.
While the experts argue, you and I are allowed to feel the thing. So let me set the coin back in front of you and tell you honestly what I see when I look at it now. First, the honest ledger one last time so nobody walks away misled. What is measured? A universe flat to 0.5%, rippled at 1 part in 100,000, matching inflation's fingerprint in detail. What is inferred? That flat space, read simply, runs on without end. What is assumed? That matter out there explores its possibilities the way the ripples here suggest. And what is concluded, if every link holds? The copies, the abundance, everything this video promised. 4 links in decreasing order of certainty. That ranking is the real lesson of tonight, more than any single wonder. Because knowing which parts of a beautiful idea are measured and which are hoped is the difference between understanding science and merely being dazzled by it. I see an object my instincts insist is scarce, and my instincts are not wrong here, in this room, in this region. Everything scarcity ever taught you remains true in the only volume you will ever touch. The model does not hand you a refund, but if the simplest reading of our best measurements is right, then the scarcity I feel is a fact about my location, not a fact about reality. It is the truth of one parking space in a lot without end. Somewhere, at a distance I can write but never feel, the pattern that is me diverged and diverged again, endlessly, into every life I did not live. Versions who never missed the chance. Versions for whom the word enough never had to be invented. When I first understood this, I had to sit with it for a while, not because it felt like winning something, but because of what it does to the meaning of a life like mine and yours. Think about what it does to the idea of failure, for instance. In this picture, every risk you ever weighed and declined was taken, by a version of you somewhere with every possible outcome. Every path not walked is being walked. There is a strange comfort buried in that, and a strange sting. The comfort that nothing possible was ever truly lost from the universe's ledger. The sting that it was lost from yours. Somewhere a version of you already succeeded at the very thing you are afraid to begin, and it changes nothing you can touch. The abundance is real in the model, and the model itself makes it useless as rescue. Which is why I think the physics, followed honestly all the way down, hands back a conclusion that sounds almost old-fashioned. If every outcome happens, then what makes this one, the one being lived here by the copy watching these words, matter at all? The answer is hiding inside the physics itself. The light-speed wall that makes the abundance untouchable is the same wall that makes this room, this table, this version of your life, the only one you will ever inhabit. The copies cannot rescue you, and you cannot rescue them. Every region is on its own, which means the old instinct, tend what is in front of you because it is what there is, survives the infinite universe after all. Not as a law of physics anymore, as a choice about where to stand. And think finally about what this does to the idea of legacy, because legacy is just wealth measured in memory instead of money, and the same physics reaches it. To leave a legacy is to arrange matter, a book, a building, a family, a name in records, so that the arrangement outlasts you. In one region, that project is exactly as meaningful as it ever was. But in the endless accounting, every legacy you could possibly leave is already left, endlessly, by the crowd of you. And every one of those monuments is sealed forever inside the region that raised it, unreadable from anywhere else. No fame crosses the wall, no name is heard past the horizon. Here's the strange part. Instead of making effort feel pointless, I find this does the opposite. If nothing echoes beyond the walls, then the only place your life was ever going to matter is the one place it actually happens. Here, among the particular people who share your region and your years. The infinite universe of all things hands the local back to you with both hands. There is one more figure I want to bring into the room before we close, because he paid the full price for this idea 4 centuries early. In the year 1600, in a public square in Rome called Campo de' Fiori, a philosopher named Giordano Bruno was executed, burned at the stake by the authorities of his age. Among the accusations read against him, that he taught the existence of infinite parallel worlds. Bruno had no telescope, no satellite, no ripples in ancient light. He reasoned his way to an endless universe filled with other suns and other earths, and he would not take it back. Tegmark himself points to Bruno's case as the dark early chapter of this idea's history. 426 years later, the same idea, dressed now in measurements and counting arguments, sits inside mainstream cosmology's standard picture, debated politely in journals. Ideas can outlive their persecution. The distance between a condemned notion and a research program can be 4 centuries and 1 good satellite. So where does that leave us? Let me retrace the whole path, because it deserves to be seen as one piece. We began with a coin and the oldest lesson we know: what you have is what there is. We met the flatness problem and the December night in 1979 when Alan Guth's notebook filled with a spectacular realization: inflation, the stretching that flattens space and, in its eternal form, may never have stopped making more of it. We heard the whisper at the beach party, COBE, on an April morning in 1992, finding the ripples that seeded the galaxies, and Planck confirming the fingerprint and measuring space flat to 0.5%. We followed Max Tegmark's counting argument through the level 1 multiverse. Finitely many possible arrangements per Hubble volume, endlessly many volumes, therefore repetition. Copies of you at distances written in double exponents, and wealth as one more configuration of matter that an infinite ergodic universe cannot decline to print. And then the other hand, the light-speed wall and dark energy sealing every region into permanent solitude, and the quiet death of certainty about which copy is you. Then the honest cracks. The closed universe reading, the wraparound loophole, the unsolved measure problem, the theorem that says even eternal inflation had some kind of beginning, and George Ellis's standing challenge that infinity may never be measurable at all. And remember that none of this is finished. The 3 dials are turning as you watch this. Curvature tightening under new surveys, The topology search is pushing deeper. DESI's strange hint about dark energy hardening or dissolving with every year of data. Giordano Bruno waited 4 centuries for his idea to come in from the cold. This version of the question may be answered, in part, in our favor or against, within the lifetime of people watching this video. Few generations get to stand this close to a question this large while it is still genuinely open. Whatever the dials finally read, we happen to be alive during the measuring. Which brings us to the edge, the real one, named plainly. Every wonder in this video hangs on a single premise, that space is actually infinite. And that premise may sit permanently beyond the reach of measurement. We can measure flatness, we cannot measure endlessness. No experiment anyone has conceived can count past the horizon. Whether infinity is physically real, or only a feature of the mathematics we describe reality with, that question is open tonight, and it may be open forever. Where the science stops, it is honest to say so, and it stops exactly there. And if someday one of those dials turns hard, if curvature comes back closed, or the wraparound patterns finally appear, or dark energy's evolution rewrites the horizons, then everything in this video gets revisited in that new light. Honestly, the same way it was built tonight. That is the deal this kind of understanding makes with you. No conclusion is protected, only the method. If you like understanding things this way, slowly, honestly, with the cracks left visible, subscribe and we'll figure out the next one together. The coin is still on your table, exactly where this journey started, worth exactly what it was worth an hour ago, and, at the same time, meaning something entirely different now. One small disk of metal, in one room, in one region of a universe whose true size nobody knows. Scarcity may be a local law, but so, it turns out, is everything you will ever love. Stay curious.